Hi everybody. This is my 5th TEDx, so I must have an idea worth spreading, otherwise they wouldn't keep asking me to come and speak. So I'm going to start with a quote. Another world is possible. Another world is necessary. It's already on its way, and on a quiet day, we can hear her breathing. So why is another world possible? Why is another world necessary? Well, as you're sitting there breathing, I want you to think about this leaf, that somewhere out there there's leaves, taking in what you're breathing out and breathing it in so that they can produce more fresh air for you to breathe in. And that's extraordinary, just creating conditions conducive to life for us. So this is my passion that drives me, is how can we, in everything that we do, create conditions conducive to life? Because I'm a chemical engineer, at least I was trained as a chemical engineer, but when I saw that I had to work somewhere like that, I was very concerned about what that was breathing out. It was like Mordor to me. I didn't want to work at Mordor. I wanted to work with the trees and the water world. I wanted to make things that breathe and make life sweeter, more magic. So I went on a journey deep into the depths of the horridness of what we make as humanity, to make things that flourish, to make the economy rise, but not to make life flourish. And I was quite curious as whether I could find a solution. 10 years on, I heard a TED talk about biomimicry, and that idea just grabbed me. It was an idea so worth spreading that I flew to the Amazon rainforest immediately, as soon as I could, to go on a training session with Janine Benyus and Dana Baumeister to learn how to do biomimicry. I was there with engineers from Boeing. I was there with architects from the greatest architecture companies in the world, and we were mesmerized by the genius of life. And there, that great breathing lung that's breathing out and learning about how these creatures do what we want to do, and do it in a way that makes life flourish. Within no time at all, I was signed up for the 2-year professional training program, where we don't only go to 7 different ecosystems around the world, learning how they work and flourish, we go to the greatest designers and geniuses in the world of biomimicry, and we learn from them. When I graduated from that, I became a trainer for the program itself in the engineering section, and I learned more by teaching than anything else. So what was I teaching? What was I learning? I was learning how that other world could be possible, how we could get there. When we make things in human technology, we think we've got an innovation that's for life, yet that solar panel is like slapped on top of something, and it's made with so much energy and so much toxicity in its chemistry, and even the best of them are just not really that great, because we're focusing on just one thing. We have to start thinking how in nature the part always exists in the context of the whole. When nature captures energy, it's not just capturing energy, it's breathing oxygen. And when that leaf falls to the ground, it's building soil, okay? It's capturing energy so amazingly, and in using the most amazing technology that will blow your mind. Many of them working together to form trees that then form forests that are breathing out and producing the most amazing things, cleaning water, generating rain. And then the soil that connects all these trees together under the ground, we're forgetting all these connections that are part of what we make, and how we can also start to make those connections. So the field of biomimicry is about learning from nature, not just thinking this is a great idea out there, but how do we actually take those ideas and turn them into our world and what we make? Capturing energy, for example. There's amazing progress in the field of artificial photosynthesis. These dye-sensitized solar cells made with much lower energy, much better chemistry, and can be wrapped around things, even integrated into glass, so surfaces can start capturing energy wherever they are. Rather like leaves, as we add on leaves of our trees of existence, can they capture their own energy? As we add on developments, whatever it is, can we do that too? And everything in nature is multifunctional. Just think about the trees there. This is an idea from a company called Solar Botanic. What if our energy capture was multifunctional? These leaves that they want to put into these solar trees not only capture the energy of the sun, but also move piezoelectrically in the wind. How cool would that be? This amazing technology they're inventing. And here, the idea of solar ivy. Every surface is waiting to be capturing energy. This company called SMIT is making solar ivy, able to capture energy at different angles, at different spaces, using space so effectively. And how's this for multifunctionality? What if we integrated wind turbines and humdinger wind turbines as well into our existing electric grids? Thinking how trees think. Can we do more than one thing rather than just that? So here we have energy capturing. Can we move towards storing energy? my thesis for my biomimicry research was, how does nature store energy? And I went on a journey discovering all the ways that nature stores energy so effectively, so ingeniously, uses energy so wisely. And I translated all the biology into design ideas and into new potentials for research. And I was fascinated most by the chemistry, the potential for new batteries. Could we make batteries that are totally life-friendly? And that gets me to my greatest hero. My hero is not Spider-Man, it's the spider itself. This is probably the superhero of superheroes in the world of chemical engineering. This guy makes a material that's stronger than bulletproof vest, Kevlar. Because if you think about it, as an insect flies into that spider web, it's like a bullet flying into that vest. And it stops those insects, and then it eats those insects, and it starts to turn those insects into more spider web. Okay? What is the spider web made out of? Well, our Kevlar is made out of boiling petrol and sulfuric acid at 750 degrees Celsius in one of those Mordor-like places, and extruding it through pressure at very high pressure to develop Kevlar. What does this guy do? He uses dead insects and water. At the temperature of the body of the spider, he spins a web that is so extraordinary, so cross-linked, that is stronger than steel, 5 times stronger than steel gram per gram, 2 times more flexible than nylon. The recipe exists. People are studying it. They're figuring out how to make equivalent of spider silk now by mimicking the recipe, by following the lessons from the superhero. We can make materials at ambient temperature and pressure that are as functional as titanium. Isn't that exciting? Superhero, right? Turning carbon dioxide into oxygen is one thing that leaf does, but it also turns it into a polymer, a plastic. There's a company called Novomer that's learning that recipe, taking the enzyme in lemon peel and turning carbon from a flue stack into biodegradable, biocompatible, low-cost plastic. There's other companies using carbon as a feedstock. There's a company called Calera that turns carbon into cement by mimicking the recipe of coral reefs, which is basically what limestone is. It's ancient coral reefs. And they're doing it highly effectively. Vinod Khosla has invested in them, and they are getting really, really far ahead. What is limestone? It's basically calcium carbonate. It's carbon dioxide in seawater. And then you see shells, like this abalone shell. That's calcium carbonate integrated with proteins and these amazing composites to create a structure that is as strong as our ceramics. But we make ceramics at 2,000 degrees Celsius. This guy uses carbon dioxide instead of emitting carbon dioxide to make things. And look at that final layer, so iridescent, so beautiful. Can we do that too? Well, there's a TED talk by Angela Belcher. She talks about exactly how far they're getting in MIT with mimicking those recipes. And the final layers, what if we made the final layer like that beautiful iridescent abalone shell? This peacock's feather is not actually colored, it's brown. It just uses its final layer using nanotechnology to create these amazing structures that will reflect light to give it color. Imagine the elimination of all those toxic chemistry that we use for dyes. And what else could we do in structure? Well, this shark not only produces a skin that makes it swim really fast, emulated in the Speedo swimming costume, but its skin also prevents the growth of biofilms. There's a company called Sharklet that, mimicking that surface, creates these templates you can put over hospital surfaces, integrate into surfaces of products that will actually prevent biofilms from growing, which means all those bacteria we're concerned about, that we kill, that we keep teaching how to become stronger. This guy's been around for millions of years. He learned that killing it doesn't work. What actually works is just preventing them from forming their films. We can integrate this into our structure because we now have the technologies that we can do, which is nanotechnology. Nature's been doing nanotechnology for millions of years. The nanotechnology that will be around in the next 10 to 20 years will be the same nanotechnology that's in our cell biology. It's very exciting to recognize that from a gecko's foot to self-assembling materials to the lotus effect, all of that's been done before. We're just learning how, and we can reverse engineer that. 3D printing? You were 3D printed. It's not new. There's this amazing thing of how many layers of cells are 3D printed. This chair that was invented by a biomimicry designer is basically understanding the way cells layer so that you can generate forms with far less materials. Using the inventions of nanotechnology and 3D printing, we could be making the most extraordinary materials. Some things with amazing shapes that we couldn't do before. The shapes that we see in nature are highly efficient, extraordinarily, excitingly efficient. They've learned over millions of years to follow the path of least resistance. There's a company called Pax that makes fans and rotors and impellers and motors that are 70% more efficient, 80% more efficient, because they didn't try and make a form that would generate flow. They used flow to figure out what the form would be, and then they could 3D print the models to generate those. And then there's ways of optimizing materials where we learn how when trees grow and our bones grow, they don't add the same thickness everywhere else. They add the thickness where it's needed and evolve over time. What if we figured out where the stresses on cars would be and make them only just as thick as they need to be and take away material where it's not needed? What if we learned from the toucan, one of the toughest materials you've ever seen, yet so little material goes into making it? And then what if we actually started to learn how to cycle all materials? Nature doesn't just cycle all materials, nature upcycles materials. When you see a lot of abattoir waste lying around, the typical industrial process is let's go burn it or try and turn it into dog food. Let's put a lot of energy trying to clean it up. If you just left it there, flies would land on it, and they'd lay maggots. And the maggots would eat up all of that amazing waste till there was nothing left but maggots. And what is maggot? It's protein. If you were a chicken, you'd be very excited to have a meal of a maggot. What more is maggots have this amazing ability to withstand bacteria because they're basically pouring around in those horrible things like that. So that enzyme on their body is brilliant for wound healing. It can actually improve wound healing speed by up to 5 times. So if you dip the maggots in salt water and that enzyme comes out, you dip that into a gauze, you've got a gauze bandage that's a pharmaceutical, you've now got food for anything, even food for sturgeon. You could turn that into caviar, Imagine you could turn your waste into value. That's where we've got to start looking. And this world is starting to emerge because of our understanding that it's all the creatures in nature. The animals are just one part. The plants are just one part. It's the fungi, the algae, the bacteria, the decomposers that start to bring things back into the world so we can turn them back into opportunities. So we need to start thinking about how to manage these complex systems, making these connections, as intelligent as bee swarms are. I'm going to show you one of the newest realizations by humanity of what an intelligent species is, and it's called slime mold. There's a wonderful TED talk by a person called Heather Barnett on it, and I'm just going to show you one aspect of it. This slime mold is an individual creature, but when it starts to form connections with other creatures, it starts to look for food. Each one of those little points that you see out there is a piece of oats. It really likes to eat oats. And it'll go out and it'll find really quickly the best, most efficient, most effective pathways to those outlying areas which are laid out there by pieces of oats. What's extraordinary about this is it took 26 hours for it to get to that point, okay? 26 hours. This was done by researchers in Tokyo, the university there. And what they were doing is they took the center point to be Tokyo, and all those outlying oats were the cities around Tokyo. And what they realized is that slime mold had mapped the most efficient and most effective network for the train system that could possibly be. Without knowing it, man-made networks have already begun to replicate natural flow precisely because it is most efficient. These amazing distributed networks, instead of these centralized old ways of thinking, we need to know how to do that. It's okay. It's been done for millions of years. We just have to learn those rules and translate them into our ideas. When we start to look at ecosystems and the way they make you think, you just see networks everywhere. The part exists in the context of the whole. Every one of these networks is cascading efficiencies, cascading resources, generating more and more abundance, and generating such a rapid learning curve. We need all of that, all of those skills right now. We need to learn that as all of these species have learned, you can only be the weeds on a blank piece of land for so long. What are weeds? They're the consumers that just push resources through them, not cycling them at all, producing lots of offspring, generating throughput. Any of you heard of a species that does that quite a lot? Right? And we've got to learn that you can't keep adding mass on in a space that's limited. You have to start closing those loops and turning them into cycling. And that's what these mature forests, these amazing places, that succession can teach us how to do. We can actually generate more and more with less. It allows those limits to growth to suddenly enable lateral growth. And this is why people are starting to talk about closing loops from the linear to the circular economy. An extraordinary thinking going into that, how we can generate more and more value by decoupling resource use from economic growth. So this is where I ended up working instead. A place that breathes out, breathes in life, continues to create conditions conducive to life. I'm based here learning how the forests, the wetlands, and the grasslands actually continue to teach us lessons for how we can do it too. So what do I do about this? Every one of you loves these ideas, wants to get up and do something. I do it every day. And I find that the secret comes from the slime mold. It's about connecting, learning, and doing. Every one of you here is connecting and learning. The next step is doing. So around the world, there's many, many biomimicry networks. Biomimicry South Africa is just one of 30 in 12 different countries, over 7,000 members. This doesn't count all those researchers around the world that are doing the actual biomimicry research as well. They just had their global gathering in San Francisco this last weekend. One of the most exciting things to figure out how we as a network to start recognizing we've grown a meme that is quite amazing. So what do all of these networks do? The same as I do. We teach those young minds the magic and the wonder of nature and how much we can learn to create conditions conducive to life in everything that we do. We teach the kids that are at the best schools and at the worst schools, we teach them that when you go to university, you're still going to be learning how to make those mortal-like plants because those places haven't been taught to bring in this genius. Can we bring it in to the classroom so they know there's another world as possible? And we bring it into students as well. These students are on a workshop sponsored by a company for a design challenge. Now this company enabled them to actually develop a product that they could actually do biomimicry with. This is the company. It's an automation company, and they produce things like this. This is a robotic bird. Also, you can see it on a TED Talk. Most extraordinary things. And you should have heard the gasping of the students. Nature is extraordinary. We start to emulate its technology. What could we generate? What could we develop? And this example here is how can we access water in places that are water-starved. And the results of this competition are being announced this week as well. And then we teach professionals as well. Right here at the Innovation Hub was one of them. And then we bring people like Janine Benyus back into our country and connect her understanding of how we can learn from nature back to our own ecosystems. And we connect people back into their own ecosystems. These are professionals on a learning journey, on an expedition to Victoria Falls. We change their perceptions. You can see more through the back of your binoculars than you can through the front when you actually look up close. And we teach the game rangers themselves that every time anyone is out in nature, what could they be discovering about the genius that lies there and invention opportunities? And then we bring the doers. This is one of the greatest biomimics that I know of, Dr. Todd, who figured out how to clean water by mimicking wetlands. And we brought him to Africa's greatest wetland, the Okavango. And he was learning, and we were learning from him because we needed to start doing. This is the state of our rivers in South Africa. And this, I decided, was one of the most important areas for us to actually start doing biomimicry. So I'm going to end off with just 2 examples of how we're actually doing biomimicry in South Africa. We're learning from the genius of John Todd, how he's looked at the complex systems of learning and the detailed, intricate biological complexity in the networks of wetlands to generate these amazing eco-machines, where the final step can be fish. And those fish could be koi, and those kois eat the sludge that's typically disposed of in wastewater treatment plants. And what can you do with koi? You can sell them for hundreds of dollars. Instead of you costing money to deal with toxic, horrible sewage sludge normally, you can actually pass it through these amazing creatures and bacteria and fungi and algae that know how to transform it and end up with something you can actually sell. They did this to a canal in China, treating raw sewage, raw septage basically, pumped through that canal. And that gave us an idea. All through South Africa, there's informal settlements that are gathering and generating a lot of waste with no formal infrastructure to manage it. So what if we started to invent informal infrastructure the way nature does? So we worked with the community because you can't bring an engineering solution in to an ecosystem, to a system. We taught them how nature manages waste. We taught them how nature deals with things. And we worked with them to innovate ideas, things like those eco-machines of John Todd. And we found that some of them were innovating already by trying to sink their wastewater underground. And we started to design ideas with them. You can see here, those are those same living gutters that you saw in the canal in China. And then we designed an overarching, amazing one at the bottom that not only cleans water, generates algae for any opportunity of use, including fish farming. It produces an orchard, it produces soil, it produces compost. So the community started to generate economic benefits from actually realizing their own infrastructure, cleaning their own water. And the final step, they're cycling the waste to generate even more value, turning the waste from their system into quail eggs and things they could sell within the restaurants in the area as well. It pays for itself and regenerates the river. So our final step that we've just emerged into is designing cities for the future. What if our cities functioned like ecosystems? This was an idea I worked with one of the students on our learning journey This is a city designed in Nigeria that actually you can see it looks a lot like natural systems. And we took the lessons from that and we're now applying it. This is one of the areas in South Africa, one of the biggest cities, but you wouldn't know because we're looking at the city from the perspective of life. These are the water systems running through the city. And we sat with all the people around the city and we said, what are the biggest challenges around this place? We're developing greater than we have the capacity to supply water and to clean it and to emit that water out into the environment. And so we're working on what do the local ecosystems do? How do they generate life? Can we transfer those into design solutions? That's what the ecosystems used to be like. All that grey is the development, right? Can this development start to do what that was doing before, functionally? And yes, we're figuring out how. We're translating that genius into ideas. And then we're putting various scenarios for that city forward. And each of those scenarios has a dial that goes forward or backwards, depending on how much they contribute to creating conditions conducive to life. For us to halt the decline of ecosystems, it's necessary to think like an ecosystem. And I love this, Where New Ideas Come From, is a book by Steve Jobs. He says it comes from the adjacent possible, the future, just sitting there waiting to be birthed into the present. What I love about biomimicry is the adjacent possible is literally and tangibly adjacent and possible. It's right outside. It already exists. We just have to learn how to do it. As you go out into the world to make another world possible, which is really necessary, just make sure that it's a world that's still breathing. Thank you very much.